So in this portion of the webinar, we're going to talk about XX consensus, which is the first and only consensus protocol with the speed, scalability, and security to really support the mainstream adoption of blockchain technology. So to do this, I'm going to quickly review the requirements that we identified in the last webinar, which we view as being critical to this mainstream adoption. And then I'm going to outline the approaches that we use to meet these requirements. And once we've set some of the context here, Bernie, Mario, and myself will break down these 5 approaches at a knee-deep level, and then walk you through a simplified consensus round. So first, let's take a look at the big picture so we can see where consensus fits in. Consensus in the XX network describes the process of selecting nodes to gather transactions and proposing them to the network, where they are verified and confirmed before they become a part of the blockchain. Keep in mind, we will examine each of the subcomponents shown here, and we'll bring up this diagram periodically to kind of show you what portion of consensus we're referring to. So these are those requirements we laid out in the last webinar, and I think it's important to go through and refresh on why these are important, how they stack up with the 3 properties I mentioned on the intro slide. But I also recommend people go and watch the presentation that David gave while he received the Dijkstra Award in Amsterdam. And this should be the first video that pops up if you Google David Chom CWI. Maybe one of the moderators can throw it in the chat channel. But David does a great job of laying out the vision for the platform. So the first property we need is speed. If we're going to replace the centralized infrastructure we currently use, the platform cannot feel significantly slower than the technology we've grown accustomed to. So user experience is key to gaining mainstream consumer adoption, and part of that UX is quick, responsive apps and payments. In order to meet this, we need consensus to reach finality in seconds and support many thousands of transactions a second. The next is scalability, and you'll hear a lot about this when it comes not only in the blockchain space, but anytime you hear about consensus. And that's because it's an important aspect of decentralization, this notion of having the opportunity as a user to own and operate a node in the network. So having a large number of widely distributed nodes that are independently operated is important not only to keeping the network decentralized, but also for keeping the network robust, which is in our last property, and that is security. So robust refers to the network's ability to continue operating securely in the face of disruption. That disruption could be from malicious nodes, malicious users, an unreliable network, or even a nation-state adversary. Now, robustness combined with quantum security ensures that the wealth and data that users push through the platform remains safe well into the future. And Mario already touched on quantum security and its importance, but it's also important to note that post-quantum crypto is generally pretty unwieldy, and that's because the signatures are much larger and can only be used once. Because of this, you cannot retrofit existing platforms to be quantum secure without introducing some major performance issues. So consensus should be designed with quantum security in mind, and that's kind of what we've done here. So these are our requirements. Now we're going to take a look at the approaches we've used to achieve them. All right, so these are those 5 approaches we used to create the XX consensus. I'm just going to touch on each of these briefly since we're going to dig into them in a little more detail later on. The first is NodeCon, and this is a way to securely initialize the network and also to seed randomness we use for consensus, which is our next approach. Committed randomness is a way to generate global randomness every block, and we do this by chaining off the NodeCon random. The third is compact endorsements, and these are a way to prove finality in a compact but quantum secure manner. Fourth, and most importantly to our performance claims, is Endorser Sampling, and this uses committed randomness to select a random set of nodes to take on the resource-intensive process of receiving and verifying transactions. And last, efficient fallbacks are kind of the way we use to quickly recover from disruptions during consensus.